We're starting our journey now from the center of the Earth with the velocity that we attained from our travel from the surface down to the center. Now we're going to use that velocity at the center as our starting velocity for the new problem. So we're starting at the center with initial velocity of re square root of k. That is the velocity that we attained as soon as we pass the center. And our starting position now is at the center. So we're starting our time at the center. So time 0 is starting at the center. Now we can use the same differential equation when we do this. So in the Laplace Transforms space, our position vector, r of s, is this value that we had before. It's s times the starting position plus the initial velocity, and we have s squared over square root of k squared. Now in this case, with this new problem now, r at 0 is 0, and the initial velocity goes to re square root of k. So putting in, we get re square root of k s squared plus the square root of k quantity squared. Now this portion, if you look in a table of transforms, you'll find that this form is the sine of square root of k t. So what we're going to do now is transform back into the time domain. Now we're starting our time clock at the center, so the time is different. We'll call this t primed. We're starting at the center. So we have a t primed, and the coefficient here is radius of the Earth, and like I mentioned, that the inverse transform of square root of k over s squared plus square root of k squared is a sine of square root of k times the time in the time domain. So our new time is t primed. Now we can put this into our vector form. So this becomes r of t primed is radius of the Earth times the sine of the square root of k t primed with our ace of our unit vector. Now we'd like our time scales to match. We want to use our original time scale, so when t primed is equal to 0, our old time is equal to tc. That's the time that took us to go from the surface of the Earth down to the center. And this is where we're starting our t prime. So then t primed is equal to t minus tc, where t is going to be greater than or equal to tc. When t is equal to tc, t primed is 0. So we can now do a shift, a translation on our time. So when t is greater than tc, t primed is going to be greater than or equal to 0. So they'll match, our scales will match there. So putting in, we get r of t, our time variable that we had before, is equal to re times the sine of the square root of k. Now t primed is t minus tc, and that's in the AR direction. Now we have the sign of a difference here, and what we can do is use a trig identity to simplify this a little bit. So we have re times the sine of square root of kt minus square root of k t c in the AR direction. But we know that our tc from before is the time to the center is pi over 2 times the square root of k. That's the relationship. So k times tc or square root of k times tc is just pi over 2. So this portion here is just pi over 2. So this now becomes radius of the Earth sine square root of k t minus pi over 2 in the AR direction. Now, the sign of a angle difference is written in this form. We can write this as radius of the Earth. This is the sine of square root of k t times the cosine of pi over 2 minus the sine of pi over 2 times the cosine of square root of k t, and this is in the AR direction. Well, the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So this part vanishes, and we're left with minus cosine. So we can now write our position vector, r of t, is equal to minus radius of the Earth times the cosine of the square root of k t in the AR direction. And we can write this also in this form as minus the radius of the Earth times the cosine. The square root of k is just pi over 2 tc, so we can write it as pi over 2 times t over tc in the AR direction. Now, let's write. We'll take this now, these two forms, and we can find our velocity. First, let's rewrite our position vector. R of t is equal to minus re times the cosine of square root of k t in the AR direction, which is also minus re times the cosine of pi over 2 times t over tc in the AR direction. Now, the velocity is nothing more than the first derivative of the position vector. Well, a sub r is a constant with respect to time, so it's just treated as a constant. So when we take a derivative here, the derivative of cosine is minus sine, and then we have the derivative of the argument, which gives us the square root of k. So this becomes radius of the Earth, square root of k, times the sine of square root of k t in the AR direction. Or we can write this with that form there too. Now, to find the acceleration vector, that is the second derivative position or the first derivative of the velocity. So we can just differentiate the velocity equation. When we do that, sine is a positive cosine, and the derivative of the argument gives us a square root of k out in front, so we end up with the real part, or not real part, but the radius of the Earth, I'm thinking in terms of complex variables here, times the cosine of square root of k t in the AR direction. So those are our three vectors: position, velocity, and acceleration. Now, let's look to see what the time is to go from the center to the surface. The position vector to the surface is just radius of the Earth in the AR direction. So using this equation here, we're going to solve for the time. Remember that time here at the center, t is equal to t center. So we want to ask, what is the time to get to the surface? I'll call that ts. So r of ts is going to be equal to, we'll use this form here, well, r of ts is just REAR, that's this vector here, and that's equal to minus RE, the cosine of pi over 2 TS over TC. We put in for our time TS, time for the to get to the surface. Okay, we have our vector equation. Now we can extract out a scalar equation because the ARs are the same, the unit vectors are the same on both sides. So we get radius of the Earth equals minus radius of the Earth times the cosine of pi over 2 time to the surface over time to the center. We can divide through by minus RE, so we get minus 1 is equal to the cosine of pi over 2 times surface over time to the center. And now, to solve for the argument, we take the arc cosine of both sides. So we have the arc cosine of minus 1. Arc cosine of minus 1 is pi, and that is equal to pi over 2 TS over TC. The pi's cancel, so we get, we'll go up over here. So 1 is equal to TS over 2 TC, or TS equals twice the time to the center. And of course that makes sense. We started at the surface. It took 1 time to get to the center. That's our time TC. And then another time to get to the surface again, another TC. So the total time to go from surface to surface is 2 TC. And as before, we calculated that TC was approximately 21 minutes and 5.1 seconds. So twice TC will be 42 minutes and 10.2 seconds. So if you stepped in a hole that went through the center of the Earth, through the whole Earth, through the center, it would take you 42 minutes and 10 seconds to go completely through the diameter of the Earth to the other side of the Earth. Now let's summarize all this. So taking what we've had before, This was the first equation that we solved. The first problem was we have the Earth, we have a hole bored through the Earth going through the center. We have the radius of the Earth. Mass of the Earth is almost 6 times 10 to the 24th kilograms. And we're starting here at the surface, and we step into the hole at time equals 0. And we travel down to the center of the Earth. It takes TC seconds to do that, which figured out to be a little over 21 minutes to get there. And then we continue on till we get to the surface again. And here the time to the other surface is 2TC. Okay, so going from t equals 0 to t equals TC, so in this time interval, 0 to TC, we have these equations, which we previously figured out. Now, with the time from TC and we'll later figure out what the restriction is here on the upper end, but we know at least this is going to be at least 2TC. From TC to 2TC, from here to here, our equations now are R of t is minus RE times the cosine of pi over 2 t over TC in the AR direction, and the velocity is RE square root of k times the sine of pi over 2 t over TC in the AR direction. And our acceleration will be RE k times the cosine of pi over 2 t over TC squared. Now let's look at the resulting equations for the solution. We have two sets. We have one set of equations that's valid for time between 0 and TC, that is the time to reach the center of the Earth when stepping into the hole and traveling down through the hole to the center. And then the other equation we have is when we pass through the center and reach the other side of the Earth. And that's this set of equations where it addresses that issue. The green, this set here addresses the issue where we're coming down to the center. Now, if we look at this equation just without looking at it in depth, we see that there might be a problem here. That the position vector, as I said previously, always points outward from the center of the Earth, so always has a positive direction to it in the AR direction. So any position vector should be in the positive AR direction, but here we have a minus sign. But keep in mind that the equation is valid for times between TC and 2TC. And if we look closely here, we have the cosine of pi over 2 times t over TC. Well, t is greater than TC, so this is slightly greater or greater than pi over 2. The cosine function, if you remember, goes like this. where it goes through 0 at pi over 2. So once t is a little bit greater than tc, the cosine curve passes over into this region here. So the cosine is negative in the region where time is between tc and 2tc. So the cosine is negative, and we have a negative. So indeed, the position vector is positive. And with the velocity, if we look at the velocity equation here, we see that when t is greater than tc, we have the sine of an angle greater than pi over 2. Well, the sine curve looks like this. So at pi over 2, between pi over 2 and pi, it's positive in that region. So indeed, this equation is positive in the positive direction. So it tells us that the velocity is in the positive AR direction, which of course we see as we pass the center of the Earth. Our velocity is going outward from the center towards the surface, so it is in the positive AR direction. Now, one last issue here. Let's separate this out. Here is our solution. This is the summary of everything. Now, let's look at what happens when we move from the interior, from the center of the Earth on outward, to what happens with the gravitational acceleration. Now, remember that our gravitational acceleration equation, the scalar equation, is this: that as a function of the radial distance out from the center, the gravitational acceleration increases linearly up until we get to the surface. So this is valid for r between 0 and the surface of the Earth. Now, when r is equal to 0, g of r, when r equals 0, is 0, because there's no mass. When we're at the center, there's no mass pulling us to the center. And when g of r is at the surface, or the radius of the Earth, we know that this is just equal to little g. The gravitational acceleration at the surface, and this is k r e, and this value is 9.819 meters per second squared. And this we call little g. That is the surface value of the gravitational acceleration of the Earth. Now, we can rewrite this equation, substitute in for k. We can solve this equation here for k. We get k r e is equal to g, or k equals g over r e, and substitute it into this equation here. So g of r is g r over r e. And this tells us that the gravitational acceleration varies linearly with r as we move outward from the center of the Earth. And we can see what's going on here is when we're at the center, there's no mass, and as we move out a distance r, say where we're standing here at some distance r, we have this mass beneath us. Well, this is what contributes to the gravitational acceleration. All the mass above us does not contribute to the forces that we feel due to gravity. So it increases linearly as the sphere expands as we get out towards the surface. And then once we get to the surface, the gravitational acceleration ceases to increase because we have no more mass being accumulated as we go outside of the surface of the Earth. All of the Earth's mass has all been accumulated beneath us, and this is what gives a rise to the gravitational force that we feel. So once we leave the surface, the gravitational acceleration decreases, and we know that from Newton's gravitational force law. Is if we look at the gravitational force law for R greater than RE, greater than or equal to RE, we have that the gravitational acceleration is just the mass of the Earth times big G over R squared. Therefore, if we evaluate this at R equals to RE, we have G at RE is equal to the mass of the Earth, big G over RE squared, and we know that it also has to equal little g at the surface, the gravitational acceleration at the surface. So the two equations meet and match up right at the surface. We can solve now for MEG, big G, which is little g times RE squared, and we can now put this value in here for MEG and rewrite the equation. So this equation then becomes MEG is G RE squared, so this becomes G RE over R quantity squared. Okay, let's go ahead and summarize this. So between 0 radius at the center to the surface, G of R is equal to the surface gravity times R over RE, and where once we leave the surface and R is greater than and equal to the radius of the Earth, then G is RE over R quantity squared. And this is for R greater than or equal to RE. So we have two equations here. One is for when we're in the interior of the Earth, and one when we leave the surface of the Earth and go out into the atmosphere and space. Okay, now let's plot out the behavior of this gravitational acceleration as a function of the radial distance out from the center. If we take this as our radial distance R out, then the gravitational acceleration as we start at the center is 0, and then it increases linearly. It reaches a maximum of little g, which is the normal gravitational acceleration we feel at the center or at the surface of the Earth, and then it falls off quadratically. So in this region, G of R is little g times R over radius of the Earth. That's this. It increases linearly till it reaches the surface, and then once we leave the surface, it falls off quadratically as little g times RE over R squared. And they both match up here at the surface. That's where the maximum acceleration is. Gravitational acceleration, right on the surface. Now, one last interesting thing I'm going to talk about here is what happens in the hollow Earth. If the Earth were hollow. It turns out that inside a hollow sphere, you do not feel any gravitational forces. And I'll give you a feel for why that is. Okay, here we have spherical Earth, or just a spherical mass, and the interior is hollowed out. So we just have mass in this shell. And if we say go at any spot inside this hollow Earth, it's hollow inside here, there's no mass, and if we look at the amount of mass that we see when we view over an angle, let's say here and here. By geometry, we have two vertical angles here. Those are the same. Now, when we're offset from the center, we're closer to some mass over in here, and the amount of mass that we see that's close to us is subtended by that angle theta. And the mass that's further away from us, since the angle spreads out, we see more mass. And it turns out the amount of mass that we see increases by the same amount as the distance squared away. So they end up canceling. So if this is our distance from our point to the mass is r, you can imagine what we have is an arc length. The arc length s is proportional to r theta. So the area that we see is proportional to s squared, or r squared theta squared is what the surface area is. And then if we have a certain thickness, let's just call it delta r, then the volume, the delta volume, will just be s squared times delta r, or in this case r squared theta squared delta r. The amount of mass that we see, the delta mass, would be just the density times the volume, or the density theta squared delta r squared. Now, the gravitational acceleration, g of r, remember, is the mass, we'll call delta m, times big G over r squared. Putting in here for delta m, we got rho, the density, delta squared, or theta squared delta r squared over r squared. And we see that the r squareds cancel. So what's happening is for every bit of distance we get away from the mass, we're seeing more of it. And as we get closer, we're seeing less of it, and they exactly balance out. The amount of mass that we gain is proportional to r squared, and the force of attraction on the masses falls off as 1 over r squared. So what happens is the gravitational acceleration is constant, is the same. So for a point here inside the Earth, the gravitational acceleration towards this mass is exactly equal to the acceleration due to that mass, and they cancel. We have two vectors of equal magnitude in opposite directions, and they cancel. So we end up with no net force felt on an object inside a hollow Earth or a hollow sphere of mass. I've come to the end of this video. Thank you for joining me on this journey. I hope you've learned something here. I've gone through a lot of detail, which I will not in future videos. I wanted to go through the details so that you can see the exact steps that you need to go through to solve problems like this. But once you get used to solving the problems, you can skip a lot of the intermediate steps in the algebra. So thank you, and hope to join you on another voyage in a future video.